All right, let's start. Once again, I pulled up the exam information here. Exam is next Thursday, September 21st, 6:30 p.m. Get there a little bit before. I think they'll start the seating around 6:15 to 6:20, so get there a little bit early. And you need to be seated with your TA's recitation section. So look up where your TA's section is. And make sure you get to the right section. If you don't know where to go, first thing to do is look for your TA. If you can't find him or her, look for me. I'll be on the stage at the top of this map here. No, but your TA might assign seat. I didn't require them to do that, but some may choose to do so. But in general, no. You just got to be in the right red box. Okay, I'll have more to say about the exam next week. So right now, just focus on noting the time, location, and roughly where you need to be. All right, so today we're going to look at section 3.1. We'll be looking at derivatives of polynomials and exponentials. Okay, so what we're going to do here, we have been using this formula to find derivative all this time. The limit h goes to 0, f of x plus h minus f of x over h. Okay, we got this by looking at the picture using geometry to come up with a derivative. So this gives a very nice geometric view, but I think we can all agree that it is not very practical, right? It takes so much time to get even a simple function's derivative, and in practice, that's clearly not what you will want to do. So we're going to be looking for shortcuts. Okay, and we'll start with a very, very simple function. Very, very simple. We'll make f of x equal to 1. And let's use that formula again a few more times to get the derivative. And you're going to see a pattern starts to emerge after we've gone through this exercise. So if f of x is equal to 1, then f prime of x, according to the formula, is the limit h goes to 0 of f of x plus h. Well, 1 really doesn't care about x or h. So no matter what this changes, the function 1 is going to remain a 1. And f of x clearly is still 1 all over h. And the upstairs is identically 0, whereas h gets smaller. So 0 over anything eventually will always be 0. Okay, so that's not so bad. We'll come back to that 0 in a little bit. All right, so let's make it more complicated. Make it just x. Go through the same thing, find the derivative. Again, using the limit just for a few more times. If f of x is x, then f of x plus h is x plus h. F of x is x over h. The x's go away, h over h. Whatever h is doing, we have the same thing up and down. That clearly goes to a 1. Okay, once again, we'll come back to that. We're going to see a pattern here and then make a determination of what we notice. Let's bump it up to x squared. Okay, so if f of x is x squared, then x plus h goes in here. This becomes x plus h, the quantity squared, minus x squared over h. FOIL this out, we get x squared plus 2xh plus h squared minus x squared all over h. Simplify the numerator, the x squared go away. We got 2xh plus h squared all over h. Everything gets divided by h, so 2xh over h is 2x. H squared over h is 1h. And when h goes to 0, 2x is the thing that remains. All right, let's do one more, and then we're going to start to talk about the pattern. Let's do x cubed. Okay, so this is the kind of thing I was talking about. Doing this in practice, every time you have to do it, is really, really silly. So the goal is to find some kind of pattern. And you'll see that pattern very, very soon. X plus h cubed, that's still doable. But if you get to x plus h fourth or seventh power, for example, it gets pretty ridiculous. But cubed is still fine. X cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed over h. And by the way, you can use Pascal's triangle to get x plus h cubed to any power, actually. But that's not really important. Anyway, let's finish this up. X cubed goes away, 3x squared h plus 3xh squared plus h cubed. H goes to 0, divided by h through 3x squared plus 3xh plus h squared. Finally, these two guys with the h will go away when h goes to 0, so the only thing that stays is 3x squared. Okay, let's do another one. No, let's not do another one. I think we'll see the idea here. So let's see. With 1 we got a 0. With x we got a 1. With x squared we have a 2x. With x cubed we have a 3x squared. Okay, if you look at this closely enough, look at these 8 green boxes here, eventually you're going to notice a pattern. When we started with a 1, I'm going to write this 1 as x to the power of 0, right? And what we notice after doing the derivative is we got a 0 here. We'll come back to that. When we went to x, that was x to the first power. The derivative we got after doing the limit was x. 1. When we had x squared, the derivative we got after doing the limit was 2x. When we had x cubed, the derivative we got after doing the limit was 3x squared. Okay, so starting with the bottom, we'll work our way up. Notice what happened here. Looking at these two here, we see the same pattern. it looked like what happened is that when we took the derivative of x to the n, this thing, after the derivative, the power came to the front of it. And then the power got reduced by 1. So this was the old power. And notice that the new power is equal to the old power minus 1, right? Same thing here. Look at this one here. We started with x squared. The old power was 2, and after the derivative, the old power came to the front. The new power is the old power subtracting 1. That pattern continues here. If you look at x to the first, if you look at 1 as 1 times x to the 0, we brought the power to the front. We keep that x, reduce the power by 1. But of course, x to the 0 is 1, right? So that's why we got a 1. Same thing here. What really happened here was this. We brought the power down to the front, keep the x, reduce the power by 1. But 0 times anything is 0, so that's how we got a 0. Okay? And this is going to continue if you do x to the 4th, x to the 5th. That's the pattern that you will keep saying. When you take the derivative, it gets awfully complicated using limits after a while, but eventually you'll notice that this is what happens. The old power comes to the front. Keep that x, and then the new power is the old power reduced by 1. So we see that the derivative of x to the power of n is always n. We brought the old power to the front, keep the x, reduce the power by 1. So in mathematical notation, we'll write it this way. This funny-looking fraction-looking thing right here, this means the derivative of whatever's following it with respect to x. What that means is that we're taking the derivative of whatever's right after this thing, x to the n in our case. With respect to x means that x is the variable of interest. X is the variable we track. Sometimes we use t, sometimes we use something else, but with respect to tells you what variable is the one that we're interested in. And this is the thing that shows up down here. And this is what's called a Leibniz notation. A German mathematician around the same time as Newton that did a lot of work for calculus. This prime thing we've been using, that came from Newton. Newton gave us this prime. He actually used other symbols too. He used a dot sometimes. The prime is due to Newton. This thing is due to Leibniz. Okay, so this is really nice. This is called a power rule. With that rule, you can handle x to the n. And I showed you here x to the n, where n is a positive integer. It turns out that n can actually be any number. Can be positive or negative. Or even a fraction. It's a little bit more difficult to show that's the case using the limit. It gets a lot more complicated using limit to show this is true, but it turns out to be the case. For instance, if you're taking the derivative of, let's say, the cube root of x squared. As long as you can express whatever you are taking the derivative of in the form of x to a power, we can use the power rule. Okay, so what power would x get here? Cube root of x squared, what's the equivalent power? 3 over 2? 2 over 3? 2 over 3, that's right. This is a cube root. Cube root is 1/3 of a power, right? So that's 1/3. Okay, so let me write it down here. This is x squared to the power of 1 over 3. So that's x to the 2/3. And according to the power rule we just saw, this is going to be 2 over 3. We bring the old power to the front. Keep the x. The new power is the old power reduced by 1. So 2 over 3, x to the negative 1 over 3. And this is how you would also handle something like 1 over x squared, for example. Anything that can be expressed in the form of x to the n can be handled using the power rule. So that equivalent power for this is x to the negative 2. According to the power rule, we bring the power to the front, the old power to the front. Keep that x. The new power is the old power reduced by 1. So minus 2, minus 1. Negative 2, x to the minus 3. Okay, so the power rule is very simple, but it's also very, very useful. We can handle all sorts of things with that rule. Next thing, we're going to make this power rule a little bit more general. We've been handling just x to the n with the number 1 in front of those x to the n. Now we're going to look at what happens if we want to take the derivative of some constant, some number c times x to the n. Okay, so let's see what we're going to use the limit just one more time to see what this turns out to be. C x to the n according to the limit definition of the derivative, this is c x plus h to the power of n minus c x to the n, right? And don't worry, we're not going to expand that to the power of n here. I do notice the c, a common factor on the top. That allows me to rewrite it this way. Right? I can pull out a c from as a common factor and just leave it out. And when you take the limit, remember, any part that doesn't depend on h can be removed from the limit. So this is equivalent to c, the number that doesn't depend on h, times the limit of x plus h to the n minus x to the n, all over h. And what is that? What is that thing I put in the green box? Absolutely. By definition, this is the derivative of x to the n, right? From the limit definition. So this is derivative of x to the n, which we know is n x to the n minus 1. Simple. So what we have shown here then, following this little short exercise, is that the derivative of c times x to the n is equal to c times n x to the n minus 1. Essentially, what you do is you ignore that c, that number that doesn't depend on x, and just take derivative of x to the n, and then multiply them back together. So what this means is that, say you're taking the derivative of 3x squared. The rule says that 3 multiplied to x squared, the 3 doesn't do anything. It does not participate in the differentiation, in the derivative here. So we sidestep that 3, take the derivative of x squared, 2x, and we get a 6x. In fact, using the same limit thing we just did, we can actually show that the derivative of c times any function, not just x to the n anymore, derivative of c times f of x is equivalent to c times the derivative of this f of x, which would be f prime. And one very important consequence coming out of this is that the derivative of just the number c itself, with no x attached to it, this has no x attached to it, so it has an x to the power of 0. That makes that original n equal to 0. So this turns out to be 0. The derivative of any number that does not contain a variable is always equal to 0. Okay, so now we know x to the n, we know a number times x to the n. The next thing we'll tackle is what happens when you got things added to or subtracted from each other. Okay, so for example, derivative of some function f added to or subtracted from g of x. And then we're going to use what we already know. So I'm going to borrow the example we just did, the 3x squared example. We already know that the derivative of 3x squared from the last page is 6x. Okay? Well, we can actually choose to look at 3x squared as x squared plus x squared plus x squared, which is precisely the problem we're trying to tackle. What happens when you got these things added to or subtracted from each other? This we already know is 6x. We're using the fact that we already know the derivative of 3x squared, but writing in a different form to try to find out what we can do with this. Okay, and it looks like right here, to get 6x, all we need to do is simply take the derivative of this thing here, right? 2x plus 2x plus 2x. So these are the derivative of individual terms. And indeed, that does give me my 6x, which I know is what I should get. So knowing this as a fact and taking a guess, it seems like our guess is correct. And you can see that using other examples, it always turns out to be the case. Come up with, for example, 5 times x to the third power. You also see that this does turn out to be true. And what we then can establish from this little exercise is that the derivative of, let's say, f of x plus g of x is the derivative of the individual things and then respecting the original sign between them. Okay, so when things are added to or subtracted from each other, you simply take the derivative individually and preserving the signs between them. Plus, you keep plus, minus, you keep minus. We've got to be really careful with this. Don't carry this too far. This is only true for plus or minus between terms. If they are multiplied, for example, f times g, this doesn't carry to f times g. There's a different rule which we'll look at later. It is not equal to the individual derivative multiplied together. Same thing with division. F over g, it is not equal to the derivative individually and then put them over one another. That's got a different rule to go with that, and we'll look at those rules later on. For now, just keeping things simple, this is how we handle things added to or subtracted from each other. Okay, let's do a few examples putting all of that stuff together. Let's find the derivative of x to the power of 2 over 3 minus 5 radical x plus 1 over 2x plus 10. Okay, we know how to handle these things individually. We know if we can put them into the form of x to the n, we're done. And also, they're all separated by plus or minus. So this is a very, very easy thing to handle, just using what we have already seen. The first thing I want to do, I want to rewrite all of these things in terms of x to a power, because I have the power rule. The first one is good, x to the 2/3, not doing anything to it. The second one here, this is a 5. The equivalent power to a radical is 1/2. What about the third one here? What can I do with it? I can bring the x to the top. What about a 2? What you should do is only move that x to where you want it to go. You leave that number alone. So you should write this as 1 over 2. That 2 doesn't have anything I want from it. 1 over 2 is a perfectly fine number. I don't care about it. All I care about is x getting out of the denominator. So I want to write it as 1 over 2. That 2 doesn't contain anything of interest to me, but the x is something I can work with. I bring it out of the denominator, give it a power that's negative of whatever it was before. That 10 is a 10. 10 doesn't really do anything interesting as far as the derivative is concerned. Okay, take the derivative. They're all separated by plus and minus. We just learned that we can take the derivative individually and respecting the sign between them. So this one by itself, bring the old power to the front, keep the x, reduce the power by 1, minus, this is a constant times x to the n. That constant does not participate, so 5 stays put. We take the derivative of x to the n part, 1/2, bring the old power to the front, keep the x, reduce the power by 1. Repeat, plus 1/2 is a number just like 5. It does not participate in the differentiation, stays put. Now we look at x to the minus 1. Simple. Bring the old power to the front, keep the x, reduce the power by 1. Okay, and what does 10 turn into? 0. I'm sorry, here's a prime here, sorry. Right, there's no x in here. Anything without a variable attached to it is considered a constant. A constant doesn't change. Derivative is talking about the change, the rate of change of something. It doesn't change, so it has no rate of change, 0. Good. Okay, let's clean this up a little bit. This is 2 over 3, x to the minus 1/3, minus 5 over 2, x to the minus 1/2, minus 1/2, x to the negative 2. This is perfectly fine, but you could also write this as 2 over 3, cube root of x downstairs, minus 5 over 2 over radical x, minus 1 over 2 with the x squared downstairs. As far as I know, WebAssign doesn't care which of these two forms you put in. But you need to be aware that you could also choose to write it this way and vice versa. Any question on this example? Okay, good. Even though we cannot handle a general case when f and g are more general functions, we can handle some specific cases where they are both some forms of x to the n. For example, let's say y is equal to x squared times the fifth root of x. Okay, so even though we got two things multiplied, and in general we cannot just take the derivative individually and then multiply them back together. But in this case, they're both in the form of x to a power. We could actually rewrite them into one as one term. Okay, so this is equivalent to x squared times x to the 1 over 5. And that is equivalent to x to the power of 2 plus 1 over 5. You have the same base, and when you combine them, you add the exponents they come with. So we keep the same base, which is x, and we add the two exponents, 2 plus 1 over 5, which is equal to 11 over 5, I think. Yeah. Okay, so this turns out to be nothing more than x to the 11 over 5, and that's something we know how to handle. That is actually really, really simple. Bring the power to the front, keep the x, reduce the power by 1. 11 over 5 minus 1 is 6 over 5. And once again, you can choose to write this as that or the 6th root of x to the 5th. No, I got this backwards. 5th root of, 11 over 5, x to the 6th under a 5th root. Sorry about that. And you know that because you look at the denominator of the power, that tells you the root. So this is a 5, tells me I need a fifth root. And whatever this thing is on the top can go with the x. And again, WebAssign doesn't care which of these two forms you write, you give your answer in. But again, you need to at least be aware that this could be done. Okay, so that's simple. And that's also the same kind of thing we can do with certain cases of fractions. For example, like this one, for example. And by the way, remember, in general, we cannot say that this is the derivative of that is the individual derivatives over one another. That's not true. You can't take the derivative individually and then put them over a fraction. So that's not allowed. No. But again, we can do the same thing we've done before. We know as long as we can put this entire thing in some kind of combination with pluses and minuses of x to the n, we have no problem with it. And we've done this before when we did the limit going to infinity, right? You got multiple things over the same thing. This is equivalent to each one of them over that same denominator. And all of these guys turn into some number times x to the n with minus and pluses between them. Absolutely no problem for us. Okay, and now it's simple. We take the derivative. The number in front of x to the n does not participate, so that's a 3. Times, and what's the derivative of x by itself? 1, right. That's the second example we did today when we did the limit thing. Derivative of 5, well, that's a 0, right? And 9 multiplied by this, the 9 doesn't do anything, 9 just waits. And then x to the minus 1 is negative x to the negative 2. So in the end, we get 3 minus 9 x to the minus 2, or 3 minus 9 over x squared. All right, so fractions and multiplication, just make sure you put them into some form of x to the n, added to or subtracted from each other. And then everything from there is very simple. Okay, let's talk about this e to the x thing that we've seen quite a bit. We're trying to find, we've encountered e to the x, and we know e is a very special number. Now, it turns out that it has a very important consequence when it comes to the derivative of e to the x. So we've got to think back a little bit. The way we define e was that we define e as the number such that e to the x has a tangent line slope of 1 at the point 0, 1, the y-intercept of e to the x. That was the way we defined e way back then. E is somewhere between 2 and 3, such that it would have a tangent slope exactly equal to 1. That's e to the x. And the tangent line right here, slope is equal to 1. So what this means is that f prime of 0, and this will be the last time we do this limit thing in class, I promise. No, wait, I lied. We'll use it a few more times, but it won't be very often, I promise. So remember, using the limit form, we can say this is equal to f of 0 plus h minus f of 0 over h, right? F of x is e to the x, so e raised to the power of 0 plus h is e to the h. E raised to the power of 0 is 1. So what we learned that we know the derivative at 0 means the slope of the tangent line at 0. That we know from the definition of the number e is going to give me a 1. Now, using that fact, the middle limit here turns out to be this funny-looking limit that we haven't seen before. So let's leave that because we'll need that in a little bit. This funny-looking limit turns out to be 1. So let's tackle the more general problem. Now we can say that if f of x is e to the x, then f prime of x, by its very definition, if f is f of x plus h minus f of x over h. Which is equal to e to the x plus h minus e to the x over h. That's still not going to get us anywhere too useful yet. Let's rewrite e to the x plus h as e to the x times e to the h. And then what I notice is I have a common factor of e to the x within the limit that I can factor out. Right? I pulled out e to the x from here and e to the x from here. And just like when we dealt with the c times x to the n thing before, anything that does not depend on h can be pulled out of the limit. So this guy comes out. It doesn't have any h in it. It doesn't do anything useful inside the limit. Now we come to this funny looking limit that we actually saw just a minute ago. Right? This guy is equal to 1. So this green box right here is 1. This is going to turn out to be e to the x. And what this tells us, the important thing is the derivative of e to the x is itself. Okay, that's a really, really nice result. The number e is very, very special. It would, because it has a slope of 1, using that, we can see that it's going to be its very own derivative. Now, if it's e to the 2x and e to the x squared, that's a different story. But e to the x itself is just e to the x as a derivative. And no other number has that property besides e. Okay, the last thing we're going to talk about is, if you look at the function y, is f of x equal to x to the 4th, for example. I can take the derivative of that. We know how to do it now. It's very simple. By the way, there are other ways to write the derivative. Sometimes you see dy dx. That d dx means the derivative of what? Of y. Okay. So that's 4x cubed. We know that already. Now, if you look at this thing right here, this is no different than x to the 4th fundamentally. There's nothing stopping me from taking another derivative. So in fact, I can do it again. If I take the derivative of a derivative, I just keep adding these primes to it. The derivative of y prime is y with 2 of these things. We read this as y double prime. That's the same as f double prime. The Leibniz notation looks a little weird. To indicate second derivative, we put a square with a d on the top, but we put a square with the x downstairs. So it's a very strange looking thing, but that's just the way it is. It means that the same thing as y double prime or y or f double prime. So this would be 12x squared. And the first time you take the derivative, we call that the first derivative. The second time you take a derivative, we call that the second derivative. Let's keep going for a little while. Right? We're going to do y triple prime, f triple prime. And once you understand how the Leibniz notation works, any derivative beyond that is simple. 24x. This will be the third derivative. In the Newton notation, beyond 3, you no longer add these primes anymore. Imagine taking the 10th derivative, you put 10 of these things here, then you got to count that. That's really silly. So beyond the third one, what we do is we put a number in parentheses to indicate that. We don't put any more primes after the third one. It's not practical, and it's very cumbersome to count. But Leibniz notation is very nice. You just simply bump the power up. So that would be the fourth derivative. And you can do this in principle for as long as you want to. Now in practice, what are these things doing? Let's suppose that y is telling us the distance / displacement / position where things are. What's the derivative of that? Velocity, right. So the first derivative of a position is velocity. What about the second one? Good. Acceleration. What's the derivative of acceleration? Jerk. Good. If you didn't know that, that's okay. It's not something that you use very often in practice. One instance where I know that where jerk comes into play is when you design roller coasters. You want to keep the jerk under a certain number. Otherwise, the change of acceleration being too great means that it can actually do harm to the human body. It could, for example, dislocate a vertebra in your neck, for example, if the jerk is too high. So that's one case that you want to keep it low. Anyone know the derivative of a jerk? Good, very good. Jounce. Sometimes called snap. Again, that's the kind of thing that even if you don't know that, it's not a big deal. The minimum you got to know is that the derivative of position is velocity. The derivative of acceleration of velocity is acceleration. Okay? All right, that's it for today. See you Monday. Have a good weekend. That's indicated. So you see the PV, it's always being derivative of something. Okay. Now sometimes we put it right after that, but we could also
try this again.